Okay, so what if I told you that the ancient art of paper folding and the fundamental laws of particle physics are connected? I know, it sounds like something straight out of science fiction, but today we're diving into a real-life link between the delicate creases in a piece of paper and the incredibly violent collisions of subatomic particles. It's a discovery so unexpected it completely rocked two different fields of science.
So let's just get right to the big question hanging in the air. How on earth could folding paper possibly teach us anything about what happens when particles smash into each other at nearly the speed of light? I mean, on the surface, it sounds absolutely impossible. But as we're about to find out, the universe has some pretty wild secrets hidden in the most unlikely places.
You know, this quote from mathematician Pavel Galashin, it just perfectly sums up the sheer shock of this discovery. Finding this connection was, for him, like spotting a mythical creature in the middle of a crowded city. It was something that, by all logic, just shouldn't be there.
All right, so to really get why this was such a mind-blowing moment, we first need to appreciate the massive puzzle that physicists have been trying to solve for decades. And that puzzle is all about predicting what happens when particles collide. To get into that puzzle, you have to know about one of the most crucial calculations in all of physics. See, when tiny particles smash together, they can do a bunch of different things: bounce off, change direction, or even create totally new particles. The scattering amplitude is, put simply, a number that tells you the odds of any one of those things happening. Getting that number right is, well, everything.
For a long time, the go-to method for this involved something called Feynman diagrams. But here's the problem. Even for pretty simple collisions, this could mean adding up thousands, sometimes even millions of different mathematical terms. A newer, better method still required hundreds of steps. And this is where it gets weird. After all that ridiculously complicated work, the final answer was often shockingly simple. It was a huge hint that the math was hiding a secret, a much easier path to the answer.
Well, that hidden shortcut finally started to show itself back in 2013. A totally revolutionary idea came along that transformed this messy, ugly algebra problem into a beautiful question of pure geometry.
The big breakthrough really came from an incredible coincidence. Back in the early 2000s, a mathematician was studying this purely abstract geometric space, totally unrelated to physics. Then, about a decade later, two physicists realized that the diagrams they were using for their particle collision math looked exactly like his. This wild, out-of-the-blue connection led them to define a brand new geometric object. They called it the amplitudahedron, and seriously, the best way to think about it is like a beautiful, multi-dimensional crystal. Instead of doing pages and pages of brutal calculations, you could just calculate the volume of this shape, and boom, there was your answer. It was like a cheat code for physics, turning horrible algebra into elegant geometry. But, of course, there was a catch. For this new idea to really change the game for real-world particle physics, a crucial piece of the puzzle was still missing. The physicists had to prove something really fundamental about the shape's basic structure. So the big nagging question was this: could their geometric jewel be broken down neatly into simpler pieces? You know, like a Lego model, where all the blocks fit together perfectly with no gaps or overlaps. It's a mathematical idea called triangulation. If the answer turned out to be no, then this whole beautiful geometric vision might just fall apart. For more than a decade, that question just hung there. And the answer, incredibly, didn't come from a bigger particle collider or some supercomputer. Nope. It came from a piece of paper. Now, it's really easy to just think of origami as a simple craft, right? But that is a huge mistake. The mathematics behind paper folding is an incredibly deep and complex field. Just figuring out if a pattern of creases can actually be folded into a shape without ripping the paper is a seriously hard computational problem. This isn't just art class, it's hardcore math. So how do we get from a folded paper swan to a colliding subatomic particle? Well, the connection was spotted by a single mathematician who saw a pattern that literally no one else had noticed before. And this is the moment everything changes. In a very recent paper, that mathematician Pavel Galashin published his findings. He revealed the link. He'd found the Bigfoot in Manhattan that connected these two completely separate universes. Okay, so how in the world did he build this bridge? Conceptually, it's wild, but it works like this.
You start with just the outer edge of an origami crease pattern. For every little segment of that edge, you record its position before you fold the paper and then its position after you fold it. Then you combine all that before and after data into one single mathematical point. And here's the absolute magic. That single point, which came entirely from paper folding, lands perfectly inside the amplitudahedron, the geometric shape that describes particle physics. The sheer elegance of this was just breathtaking. Nima Arkani Hamed, one of the guys who discovered the amplitotron in the first place, said this about Galashan's work. It provided a totally new and shockingly simple way to define this incredibly complex object. It turns out the shape of particle physics was secretly the shape of paper folding all along. And look, this wasn't just some cool, oh, that's neat kind of discovery. No, this origami connection was the exact tool that physicists needed to finally solve that decade-long puzzle about the amplitude-hedron structure. Using this amazing new connection, Galashan built an algorithm. For any point you pick inside the amplitude-hedron, his algorithm could spit out one, and only one, valid origami crease pattern that corresponded to it. This perfect one-to-one mapping was the key. Because every point inside the shape could be matched to its own unique crease pattern, it proved there could be no overlaps between the building blocks. The algorithm also showed there were no gaps. Everything fit together like a perfect puzzle. The triangulation conjecture was finally proven. Their geometric jewel was flawless. So why is this such a big deal? Well, for starters, it solved a major decade-long mystery in physics. But at the same time, it also solved a completely separate, long-standing problem in the mathematics of origami. It built this stunning and still kind of unexplained bridge between two totally different worlds. And it's given physicists a brand new way to think about the fundamental geometry of our universe. And that just leaves us with this one last incredible thought to chew on. If the deep rules for colliding particles are somehow encoded in the folds of a simple piece of paper, what other profound secrets about the cosmos are hiding all around us, in plain sight, just waiting for someone to notice the pattern?